How is everyone?
Pretty good.
Most of you I just saw like in the past few hours, but I'll ask anyway. All right, let's see. So I graded your first homework assignment and handed that back on Canvas. And I looked at a number of problems on there since a lot of the problems were pretty short. And no real concerns in any of that. So let me just reiterate a few things that I saw. So section 1.1, I looked at question 2, which was defining listing the elements in a set. So a few people had some confusion about C. So C is written kind of funny. It says the set of minus K such that K is in the set P. And the way to think about these is, start off and take everything that's contained in the set P. So pick one thing from the set P, call that K. Minus K will be in our set. Pick another thing from the set P, call that K. Minus K will be in our set. So P is a set of positive numbers. If you use primes, that's okay. But P means positive integers. And so, for example, 1 is a positive integer. So K could be equal to 1. So minus 1 is in our set. And 2 is a positive integer, so K could be 2, so minus 2 is in our set, and so on and so forth. So it's not asking for the set of K and P such that K is minus, something is some negative number. It's saying it consists of all minus K such that K is in the positives. And it's the same thing here, right? The set of n squared such that n is one of these. Well, set n equal to minus 2, n squared is in your set. That's the number 4. Set n equal to 0, n squared is 0. That's in your set. Set n equal to 2, n squared is 4. That's in your set. Well, we already named that one. So that's just the elements 0, 1, and 4. And then set of positive integers that are a factor of 24. So factor means it divides into 24. So 1, 2, 3, 4, 6, 8, 12, and 24. As opposed to 48, 96, 240. Those are multiples of 24. And we'll work a lot with factors in another week or two when we get into some number theory. And we'll play with divisibility and the notion of what divides what a great deal. All right, and then section 1.2, I looked at question 4. And this was the one that we talked about in class about giving examples to illustrate the following facts. So, our universe is the set of positive integers from 1 through 9. And, A is a subset B, B is a subset C, A is a subset C. So most people picked, 1, 2, 1, 2, 3, and 1, 2, 3, 4, something like that. That's fine. We worked through this one in class. That's fine. It's interesting because for C, about half the class changed A and B and changed the universe to be the numbers 1 through 6 and just kind of forgot about 7, 8, and 9. I don't know why. But the idea here was, pick a set A and a set B such that their union is equal to the universe, right? This is the universe. And their intersection is empty. So A could be, the odd numbers and B could be the evens, or A could be 1 through 4 and B could be 5 through 9. Or whatever, right? But, pick sets A and B so that, the universe is equal to their union, the intersection's empty, and then show the universe minus B is equal to A. So I give a lot of wiggle room on that because there seemed to be some confusion. And then 1.3, question 2. No, I didn't do that one. 1.2, question 6. So this is about infinite sets. And this was the one that was kind of the most strange of all the questions. So suppose U is an infinite universal set. So we're thinking of some universe with an infinite number of things in it, like the integers, for example, right? And suppose A and B are infinite subsets, so they're really big pieces of U, right? So must the complement of A be finite? So you have an infinite set, and now you throw away all those infinite things. Are you guaranteed to be left with a finite collection? And it may feel like that's a reasonable conclusion, but it's not always true. For example, suppose the universe is all integers, A is the even integers, and B is the set of odd integers. Well, the complement of all the even integers is still an infinite set. It's the set of odd integers. And so even though we throw away, an infinite number of things from our universe, we might still have an infinite number of things left over. On the other hand, A could be the set of all non-zero integers, and then the complement would be just a singleton containing the number 0. So the complement could be finite, could be infinite. So the answer here is no, that's not a true statement. The union, on the other hand, is guaranteed to be infinite. Because A union B means start with A, which is already infinite, and then maybe add some extra stuff, right? So it's only going to get bigger. So for B, the answer is yes. And then must the intersection be infinite? Well, again, think of the evens and the odds. What's the intersection of those two infinite sets? It's the empty set, which is definitely finite. So this is no, yes, and no, if you just want the punchline.
So for A there, when it's asking about A is the complement, because B is also an infinite subset, that's why it cannot be finite ever?
It could be. For example, in the universe of all integers, I could make A the set of all integers different from 2, right? That's an infinite set. The complement is just the set containing the number 2. So in that case, the complement would be finite.
I guess A confused me a lot because I made the assumption, which is probably, it could be true, could be not true, that A and B don't overlap, so that anything that is in A is not in B, and anything that is B is not in A, which is not a good assumption, thinking back on it.
Right.
But if that were the case, I was assuming that the complement of A would always be infinite because B is infinite.
But B isn't even mentioned in part A, right?
Right.
And
it could be a
so
infinite subset C, right?
Yeah. So A could be the set of every number except the numbers from 1 through 10. And B could be the set of containing 2 and 3. Oh, B is an infinite subset. So, but B could be something else, right? So yeah, the complement, we can't say that that's finite or that it's infinite. And the only one we know has to be infinite is the union. In 1.2, was A, B, C, comma, C in exercise 4 supposed to carry over the definition provided in exercise 1? I don't think we carry over definitions. Let me see what we're talking about. So 1.2, exercise 4, supposed to carry over the definition provided in exercise 1. No, this question has nothing to do with question 1. Yeah, I mean, it's a totally different question. But for every question for every part of question 4, right, the universe is equal to 1 through 9, right? That applies to all 4 parts. I didn't take off points if you change the universe, but Other questions on this homework?
Are you going to give us the answers to 1.2 number H?
1.2 number H.
Oh. The university students question. You said we were going to come back to it, so.
Well, we're going to come back to it when we talk about counting in a few weeks. But we can talk about this now. So let's at least sketch this a little bit. So your universe consists of 16,000 students. You got 9,000 day students, 300 math students, and 1,000 graduate students. 250 day students who major in math, and so on and so forth. So what are we doing here? Oh, my camera disappeared on me again. Hold on a sec. Nope, that didn't work. All right, my machine is not having a good time. So I'm going to take that out and try to just do the doc cam. Oh, denial. Trying to get my document camera working right now, and it's not being very happy. So let me turn off my share. Dang, all right, I'm going old school. Hold on one sec. Well.